So first, anybody have any questions about homework? Yes? Okay, you have it in front of you. Anybody? No, I don't have the date on the top of my head, but it's if you look on D2L in the announcements, all the assignments in parentheses say when it's due. So you'll just take all those, staple it together, and turn it in at the end. Yeah. Yeah, right. So no, turn it in on the date in the parentheses in the title. I assure you, it's all my intentions are all very clear to me. Yes. That is. Yes. I don't. Okay, upcoming Wednesday. Okay. It's a. Yeah, it's a. I don't have them. I can't remember them all. But yeah, with all three of the classes I'm teaching, it's pretty clear in the announcements in the title. Okay, number 6. Oh yeah, number 6. So the question says d dt of the quantity 2xt squared is equal to 50. Where at time equals 1, x is equal to 5. All right, so is this an ODE or a PDE? Oh. And what are the independent variables? Just t, it's ODE, so it can only have one. What are the dependent variables? Yep, x, and that's what we're trying to find, the function x of t. What's the order? First, yep. And so we need one boundary condition. We have one, so it looks promising. And now, okay, what's the first thing you would think here? Well, the first thing you would probably think is, this is a weird form. I'm gonna distribute that derivative operator out through everything and see what the equation really looks like. So and so if you take that derivative, you get, let's say 2 times dx dt times t squared plus 2x times 2t is equal to 50. Okay, so I'll rewrite that as 2 dx dt, let's do it as 2 t squared dx dt plus 4xt is equal to 50. Okay, well, all I'm asking you to do with differential equations is separation of variables. So now the question is, can you solve this with separation of variables? And you can try a few different approaches, but you're never going to be able to separate it into all the x stuff on one side and all the t stuff on the other side. Okay, so what are you going to do instead? So instead, we're going to make a substitution. So we'll define a new dependent variable. Mhm. Because you could do that, but you don't know what x is. That's a function you don't know. You know, so when you tried to take the integral of this thing, you know, right, and we don't know what it is. Yeah. So we'll define a new dependent variable. You can call it y or z or whatever you want. But let's say y, which is a function of t in the end, that's equal to all that stuff in the parentheses, 2xt squared. I'm writing this as y is only a function of t because x is also a function of t. We just don't know what it is yet. Okay. And so now we can rewrite this equation, ordinary differential equation that we started with, as d dt of y is equal to 50. Now this we can, so on the boundary conditions, let's wait on those on a second. We'll deal with this later. So this is easy to solve. It gives you that y is equal to, let me not skip that step. So we get dy is equal to 50 dt. Integrate both sides, and you get that y is equal to 50 t plus c. And now we can substitute back in for y. So 2xt squared is equal to y, so we get 2xt squared is equal to 50t plus c. And now our boundary condition says when time is equal to 1, x is equal to 5. So x equals 1, no, x equals 5 corresponds to t equals 1. So plug into this equation, and you get 2 times 5 times 1 squared is equal to 50 times 1 plus c. So 10, this should have been 1. So 10 is equal to 50 plus c, and so c is equal to negative 40. And so our updated relationship between x and t says 2x t squared plus 50t minus 40. What am I doing here? This should have been equals. Okay, so that's a perfectly final relationship between those two, but it'd be nice if we could write x as a function of time. So just divide everything through by 2t squared, and you get x of t is equal to 25 over t minus 20 over t squared. Any questions about that? So if you ever see a problem where you're taking the first or second derivative of a hunk of stuff like that, just substitute in for the hunk of stuff. You can solve the problem and then substitute back at the end. Okay. Yes. The integration method. Okay. That doesn't occur to me how you would do that. So you integrated. Oh, okay. Yes. Okay. So you. Okay. So you have the derivative of all this stuff, 2xt squared dt is equal to 50. Okay. Yeah. So really, that's what you're doing. I just took the extra step of redefining this as a new variable. So, okay, yeah, so when I said it wouldn't work, right, I was thinking about this wrong. What you really have is an increment of this whole thing. And you can think of it as, you're basically doing this separation of variables, where this whole thing is your increment. That's what, in the one above, I called dy. So if you take that, if you integrate that, you get 2xt squared is equal to 50 t plus c, and you get the same thing. I just took the extra step of calling this something else because we're not used to taking an integral with respect to a hunk of stuff like this. And, okay, so I'll never ask you to recognize anything more complicated than this. So in this problem, it was given to you that you have a total derivative of a hunk of stuff, and so just make the substitution, go through it, substitute back at the end. That's all I'll ever ask you to do. But notice that so notice how could I make this problem look harder? That's sort of like a classroom, school way of thinking about this. But another way to think about it is, how could this, what's another way this same approach could arise, like in the wild, in a research project or at work or whatever? And the answer is, what if you got this differential equation, 2t squared dx dt. So 2t squared plus 4xt is equal to 50. Is that what it was? where x of 1 is equal to 5. Well, we just went through the steps backwards that showed that this is the same problem as that. But it's trickier to recognize this. Yeah, I just forgot to write that. dx dt, thanks. Okay, so that. And then you would have to recognize that 2t squared dx dt plus 4xt is equal to dx dt of x squared of 2x squared t. Okay. And if you're not looking for it, it would be hard to, this would be an easy thing to miss. But if you did, if this problem did come up, and you did happen to notice that this expression can be rewritten as a total derivative of a hunk of stuff, then you can solve it using that substitution method that we did this problem with. Okay, thank you. Yeah. And that's actually one of the re-expressing problems like this as a total derivative of a bunch of stuff is actually one of the 50 or 100 techniques you learn when you take differential equations. And then you forget them quickly after the class finishes, but that's one of them. All right, any other questions about homework? Yes. So number 11 is kind of an exercise in chain rule, product rule. So we have this vector u that's equal to xy is the x component and xy squared is the y component. And x is a function of time and y is a function of time. And we want to take the derivative with respect to time. So we're taking the derivatives of these two expressions, separately. The time derivative of xy is going to give us the x component of the derivative. The time derivative of xy squared is going to give us the y component of the derivative. And so what we're going to have to do is use product rule because we have these things multiplied together, and chain rule because x is a function of time and y is a function of time. Okay, so let me show you why the chain rule thing happens. So dx dt, no, that's not why. So we're going to have to do the product rule. Which says that ddt of like x times y is equal to derivative of x times y plus x times the derivative of y. And for the y component, the product rule says derivative of xy squared is x dot y squared plus x times y squared dot. And then the last thing that we're going to have to do is the chain rule. Because the time derivative of y squared, I'll write it like this, is the derivative of y squared with respect to y times the derivative of y with respect to t. So if we put all this together, we get that u dot is equal to, for the x component, x dot y plus xy dot. And for the y component, we have x dot y squared plus, and now we have x times y squared dot, but we have to substitute this stuff in. So we have x times, what's dy squared dy? 2y, yep. And then dy dt I'll write as y dot. And you can simplify that a little. You get an x component of x dot y plus xy dot, and a y component of x dot y squared plus 2xy y dot. Any questions about the thinking on that one? Any other homework questions? Yep. 8. So that one says t x double dot is equal to t cubed. Oh, 8. And the issue there comes up when you get to the boundary conditions, right? Is that where you got sort of didn't know what to do? Okay. Okay. 50% chance it's you, 50% chance it's me. Number 8. No. Okay, I lost the 5 already. Maybe that's how. Number 8. 5t squared x double dot is equal to 50, where x of 1 is equal to 2 and x of 10 is equal to 20. Okay, it's an ODE. Independent is t, dependent is x. Second order, so we need 2 boundary conditions, so it all looks good so far. Yes? No, it doesn't have to be. And so we'll, so sometimes it is, sometimes it isn't, but we can do it either way. So I'll show you how to do that. I'm going to rewrite this as 5t squared d dt of x dot equals 50. And so we have dx dot is equal to 10 t to the minus 2 dt. And so integrate both of these, and you get x dot, x dot is equal to negative 10 t to the minus 1 plus c1. Any questions so far? And now I'll rewrite that as dx dt is equal to negative 10 to the minus 1 plus c1 dt. Separate variables, you get dx is equal to the quantity negative 10 t to the minus 1 plus c1 all times dt, and you can integrate both of those. So x is equal to negative 10 natural log of t plus c1t plus c2. And now we'll go boundary conditions. So boundary condition 1 says when t is equal to 1, x is equal to 2. So 2 is equal to negative 10 natural log of 1 plus c1 plus c2. Natural log of 1 is 0. So our first equation says c1 plus c2 is equal to 2. Call that equation 1. Everyone okay with that? And then equation 2, boundary condition 2, says when t is equal to 10, x is equal to 20. So plug those back into this same equation. We get that 20 is equal to negative 10 natural log of 10 plus 10c1 plus c2. And so our second equation says 10c1 plus c2. Can someone calculate 20 plus 10 natural log of 10? Okay, so this is equation 2. Was there a mistake I made that showed up here from before? That's what you got, okay. And that's not what I got. Okay, that's a serious indictment on my answer in the solutions. Okay, someone email me that, please, and then I'll remember to fix it. All right, so now what you have is a system of two equations. Two unknowns. Your unknowns are C1 and C2. C1 plus C2 equals 2, and 10C1 plus C2 equals 43.03. You know, I don't like to think. I like to just have things that I apply the same way over and over again. So I tend to solve this by reduced row echelon form with my calculator. But if you're one of those people who like to think about stuff, you could subtract this equation from this equation. So you get negative 9C1 plus 0 is equal to negative 41.03. And then what's 1.03 divided by 9? 4.56. And so then C2 is negative 2.56. And so your final solution says X is equal to negative 10 ln t, negative 10 natural log of the absolute value of t. Well, we're talking about time, so we're never going to have negative times anyways, so I'll just leave that off. Plus C1t plus C2, so plus 4.56t minus 2.56. Any questions about that? So yeah, it's an important thing to notice. Those boundary conditions don't have to be one for derivative and one for the function itself. They can both be, well, they can't both be for the derivative, but they can be both for the function, and then you just have to solve it as a system of equations. The order, no. I mean, like which boundary condition you do first, right? No, doesn't matter. All right, any other questions? Homework questions? Yes. Oh, yeah, okay. So, how many people here have done matrix multiplication before? We'll do some of it in this class, or there's some people who haven't. So if you're multiplying, okay, so number 5. If you're multiplying a vector times a matrix, let's say we have a matrix A, B, C, D, and we're multiplying it by the vector E, F. Then you get a vector out that's equal to AE plus BF. That's the first component. And the second component is CE plus DF. So that's how you multiply a matrix times a vector. Okay, so let's multiply out this this system of equations in number 5. It says x dot y dot is equal to the matrix 0 t 2t, and then negative t 0. That's the matrix, and multiplied by the vector x. So we're just going to multiply out this matrix and see what system of equations we have. So we get that x dot y dot is equal to 0 times x plus 2t times y. And then for the second component, we have x times negative t plus 0 times y, so negative tx. Okay, that's a system of two equations. X dot is equal to 2ty, and y dot is equal to negative tx. And why can't we solve that? What? Those are coupled. And they're coupled because there's y's in the x equation and x's in the y equation. That's actually not a complicated equation to solve, but we're not dealing with coupled systems. Any other homework questions? Okay. So let's start going with particle kinematics. It does have mass, but yes, infinitely small. So yeah, so let me remind you a little bit. So a particle, when you're treating something as a particle, you're treating it like the object has mass, but no length dimensions. And since there's no length dimensions, there's no way to differentiate between a left and a right and a top and a bottom. Okay. In other words, we have no way to track the orientation of the object. So when we're doing particle kinematics, all we're doing is tracking the location of a point as it moves around. So some people think like you do particle physics when an object is really small, and there's some truth to that. Probably the smaller an object is, the more likely you are to treat it as a particle. But when you're doing celestial mechanics, you're tracking planets and stars, treating them as particles because you just don't care about the orientation. You only care about where they are in space, and obviously those are really large things. You just treat them as a particle because the orientation doesn't affect what you're trying to do. Well, I mean, they have features that you could track, but if all you're trying to do is figure out how the gravity of these things is affecting the gravity of these things, and you don't care what the orientation is, the gravity always points towards the center. So I think that's, but I'm just saying that particles, you treat things as particles not necessarily because they're small. You treat things as particles because you do or don't care about their orientation. Okay. And so if this is your coordinate system, and this is your object, you're representing the location of the object by the position vector p that changes with time. Then the velocity as a function of time is the time derivative of the position. And the acceleration as a function of time is the time derivative of velocity. And that's the second time derivative of the position. Let's see. Sorry. If you're trying to go, so like talking about going from one of these functions to the other two, say, if you're going in the direction from position to velocity to acceleration, then you're just differentiating the function. And you have all the information you need if you have one of the functions. So for example, if the velocity as a function of time is equal to 2t negative t, we have that function, then we have everything we need to get the acceleration. A of t then is equal to 2 negative 1. If we're going the other way, though, that function isn't enough information. So if you're going in the direction from acceleration to velocity to position, then the function isn't enough information. You're using separation of variables. You're doing a differential equation, so you need boundary conditions. So for example, if you know that the velocity as a function of time is equal to 2t negative t, then if you went through the integration, you get that the acceleration is equal to, yes, thank you. It's a good thing you're here today. Okay, so if you're going the other way, position then is t squared negative t squared over 2, and then plus these arbitrary constants. And you need boundary conditions to find C1 and C2. Yeah, in this case, we need one for each of those two equations. It's like a system of two uncoupled differential equations. They're each first order, so we need one boundary condition for each. Yes, that's right. Exactly. So let's do an example where we derive the constant acceleration equations and let's say that the velocity at time 0 is v0x, v0y, and the position at time 0 is equal to p0x, p0y. It's constant acceleration. So the acceleration as a function of time is equal to ax, ay, where these are constants. The acceleration we know is the time derivative of the velocity. And so we get ax, ay is equal to dvx dt, dvy dt, where vx times 0 is the constant v0x, and vy at time 0 is v0y. So what we have here is an uncoupled system of first order ODEs. We need two boundary conditions, and we have them. That's what these are, the requirements that at time equals 0, Vx is equal to V0x, and the other one. So let's do the first one first. The x equation first. It says dvx dt is equal to ax. So dvx is equal to ax dt. Integrate both sides, and you get vx is equal to axt plus c1. Now the boundary condition says that when time is equal to 0, Vx is, we got to get out of here. When time is equal to 0, Vx is equal to V0x. So we have V0x is equal to 0 plus C1. So Vx as a function of time is equal to axt plus V0x. And that's the, that's the formula that you recognize from physics. Just thinking about it the way that I want you to think about it in this class. Okay, that's all. I'll put an assignment on D2L.